So back then it was like a silly idea for it, but now it's going to be very powerful because we're going to use this to set this equal component equal to another component, the x component with the x component, the y component with the y component, and that's how we're going to get our value of c. All right? So, okay, so for the first equation we get 1 equals to k times c. Well, that's one equation, two unknowns. Let's leave it for a second. Number 2, we get 4 equals to negative 2k, and 6 equals to 3k. Solving for k, you don't have to solve for k on both equations, but I'm going to do it just to verify that we just get that we get the same. So k equals to, what's that, negative 2. Did I get negative 2? Okay, no, this is negative. Oh, there was a little typo, by the way. This is supposed to be negative 6. Otherwise, it's not going to work, okay? It's negative 6. And so negative, negative 6. And k equals to negative 2. So we get the same thing, right? So now that we found the value of k, how about we substitute it here? 1 equals to negative 2c. And then divide both sides by negative 2 to get c equals to negative 1/2. So that means that if c equals to negative 1/2, those two vectors are parallel. Right? Another classical problem, okay, determine a scalar k such that the vector w, the same one for negative 6, is orthogonal to this weird vector having numbers and letters and, okay. Alright, so that it is orthogonal. Well, let's think about that orthogonality thing. How do we know if two vectors are orthogonal? 90 degrees, but in terms of the vector operations that we know, yes.
Dot product is 0.
If the dot product is 0, so that means if w dotted with v equals to 0, not the 0 vector, equals to 0 because again the dot product will give us the a scalar, not a vector. So set the two vectors, 1, 4, and negative 6, dotted with k plus 1, comma, 3 minus k, comma, 5, and let that be equal to 0. Okay? Do the dot product, k plus 1 times 1, that's simply k plus 1. 4 times 3 minus k, that's going to give us, okay, let me do 4 times 3 minus k. And 5 times negative 6 equal, that's negative 30. Oops. That equals to 0. And that's going to lead us to solving a baby linear equation. So that's k plus 1 plus 4 times 3, which is 12 minus 4k minus 30. And let that be equal to 0. Combine like terms. K minus 4k, that's a negative 3k. 1 plus 12, that's 13 minus 30, is that negative 17? Set it equal to 0, keep going. So negative 3k equals to 17, and k equals to negative 17 thirds. Alright, so we would need to substitute negative 17 thirds plus 1, 3 minus negative, or rather plus 17 thirds. That's going to ensure that the two vectors are going to be orthogonal. All right? And another classical geometry problem. Well, so we're given 3 points. Okay, 3 order triples here, for which the first two we know the 3 coordinates. However, for the third point, the third order pair, we don't know 2 of the coordinates, the y and the z coordinate. So they're asking us to find the y and z such that the points A and B are collinear. So that means, say, A, which is 1, negative 2, 3, B, which is 2, 1, 0, and C, which is 7, Y, Z. So these are 3 points that are collinear. That means they are on the same line. But how are we going to determine this? Well, actually we're going to use vectors. So we're going to use the idea that two vectors are the same if their components are equal in a similar way we did with the first example. So this is the plan right here. So I'm gonna write the vector that goes from A to B and the vector that goes from A to C. All right? You see how? Well, I mean, they're slightly shifted just so you can see so you can distinguish between the two vectors. But in reality, these are overlapping vectors, right? That's due to the points being collinear. All right. So I'm going to define these two vectors. I'm going to define vector AB. That is terminal minus initial, 2 minus 1, that equals to 1. 1 minus negative 2, that's 1 plus 2, that equals to 3. And 0 minus 3, that's negative 3. I'm going to define vector AC in this case. That's going to be, okay, terminal minus initial, that is 7 minus 1, that equals to 6. Y minus negative 2, that's y plus 2. And Z minus 3. Okay. So what are we going to do here? So the same process, okay? Because again, so AB. So okay. So these two vectors look parallel, do they? Don't they? They look parallel. So let's use the idea of parallel vectors. That means if one of the vectors, for instance, AC is a multiple of AB or vice versa. It doesn't matter where you put the K, multiplying the AB or multiplying the AC. It should work anyway. All right? So let's set it up. Okay, so that is 1, 3, negative 3 equals to K times 6, Y minus 2, or rather Y plus 2, and Z minus 3. So I'm going to distribute the K again. That's going to be 6K. K times that's KY plus 2K. Okay. Should I distribute? No, maybe I should. Anyway. And KZ minus 3K. Set it equal to the vector 1, 3, negative 3. Okay? And again, we're going to equate components by the fact that two vectors are the same if their components are equal. All right? So 6K times 1 equals to 1. So 6K equals to 1. 3 equals to KY plus 2K. Actually, I'm going to go with the factor version instead. I don't know why I distributed it. So K times Y plus 2. And negative 3 equals to K times Z minus 3. All right? So from the last two equations in are one single equation but two variables. However, from the first equation we can get that K equals to 1/6. All right? Which we may now substitute over here. So this K may be substituted there. So that is 3 equals to 1/6 Y plus 2. Negative 3 equals to 1/6 Z minus 3. Okay? And from here we can solve for y and solve for z and get the coordinate, the y coordinate and the z coordinate already. All right? So that's 6 times 3, that's 18, equals to y plus 2, and y equals to 16. 6 times negative 3, negative 18, equals to z minus 3, and z equals to negative 15. So that means, in summary, so the third point has to have a y coordinate of 16 and the z coordinate has to be negative 15. In order for these 3 points to be collinear. I mean, because if you had 2 points, only 2 points, well, their 2 points are always collinear. The minute you introduce a third point, well, they may be collinear only under one single condition, or two, or having the opposite numbers, right? So, all right. So this is the end for this handout. Now let's head